I will set about getting that ready to get that set up for Monday. And of course, if you look at the schedule, we've also got a new project here on Monday as well. Okay. Questions before we get rolling? So we're going to talk today more formally about something that I've used this word before, right? You've heard this word, dimension, and I've thrown it around rather fast and loosely. I'm going to make it more precise today. So, just kind of, what do you suppose the dimension of Rn is? Right? I use this terminology of plane being two-dimensional. What do you suppose the dimension of Rn is? This is a vector space. Here. And what is the dimension? I will tell you informally now before I make it more formal. And that is the dimension of vector space is just how big its basis is. How many elements there are in the basis. How many basis elements are there in Rn? N of E1, E2, all the way up to En. That's not the only basis, but it turns out that any basis has the same size. Let me ask you this. Y'all remember what Pnx is? These are all polynomials of degree n or less. I want to guess the dimension of this. N.
N+1.
I'm sorry.
N+1.
That is correct. Why n plus 1?
Well, because there's like the constant is the first one. And then
That's right. It starts in degree 0, right? This one turns out to be n plus 1. So this, I've probably thrown these words around, but let's make this more on concrete footing. Let me start off with Paul's theorem. Let's suppose that V is a vector space. And V a basis for V. By the way, quickly remind me what it needs to be a basis. Yeah,
that's the linearly independent span the whole vector space.
right. Linearly independent and span the whole shebang. So let's suppose you have and this is kind of a crucial course theorem. Suppose you have a vector space and you've got some basis and it's got n things in it, right? Then any set of n plus 1 or more elements of V must be linearly dependent. Well, somebody earlier in the class said this. A basis is a maximal linearly independent set. So if you've got any set that has more elements than your basis, any other set that's got n plus 1 element, it automatically has to be linearly dependent. This is not an obvious statement, but I'm going to show you why this is true. And this actually highlights some important things about what we know about matrices Rn and the connection between that and the general vector space. Suppose we have a set M plus one or more things. Suppose we have M vectors in V with so suppose I've got a collection of vectors that's just larger than this basis set. Got more elements than I've got in my original base. Everybody else do that? Now here is one of the important things about linear transformation. So consider you'll remember what these suckers are. This is just a list of numbers, right? And this is the coordinates of this vector because V1, for example, is something times this plus something times this, all the way up to something times this, right? And we make that list of numbers. And this is a vector, now it's in Rn, right? Because this is a list of the n numbers it takes to build V1 out of this list of basis vectors, right? The second list is now I'm going to build V2, which is in V, out of this list of basis vectors. And that's going to give me a stack of n numbers. And so basically what I've done is I've taken these vectors here and I've built these stacks of numbers. So now these animals all live in Rn. Do I agree with them? This is a linear transformation. So let me recall. V goes to is a linear transformation. That's from last time. So this assignment takes this to this, this to this. This is a function that is linear transformation. So how does that help us? So consider a matrix. Column vectors here. I think this is a bit of a role reversal here. What's the size of this? Okay, how many rows we got? We've got n rows because each of these things has n coordinates in it, right? And how many columns? Well, I can just count across here, right? And notice that we have an n by m matrix, and m is bigger than n. That is to say, I've got more columns than I have rows. What can you say about the columns then? If I've got more columns than rows, is it possible for me to have a pivot in every column?
No.
You got too many columns, right? So I can't have a pivot in every column. Because it's just like too many. So what does that allow me to say about the columns? The columns must be linearly dependent, correct? So let's see what that means. And this is actually the turning point, but now that I know the columns are linearly dependent, I can translate that back to the original vector, right? So what does this mean? So there are numbers, C1, C2, Cm, not all zero. Some of them might be zero, but I know for sure they're not all zero. I can find such things such that it's equal to zero back. Right. This is my linear dependent relation. Now, the fact that this is a linear transformation allows me to massage this and rewrite some of the products into this one. Right. C1, C2, C2. Yes,
Why again would that matrix have in columns?
it does. It has M columns.
Or I mean in rows, sorry.
In rows because, oh, and IRS, because what is this? So, and in fact, I'm glad you asked that because that'll give you a little reminder here. The reason for this is, what does this mean? This is a list of numbers. Let me call this different here. D1, D2, Dn. This is a column of numbers such that Di is D1, D1 plus D2, D2 plus Dn, Dn. Right? That's what this means. This means I am expressing VI in terms of my basis VI coordinates. And how many coordinates do I need? There's n elements of the basis, so I need n entries to describe it. And so it's because the basis size is n that I need these n. And that's why I have n rows. And actually, this is kind of a good segue into this, because what does this notation mean? This means that my coordinates here, of course, the zero vector means these are all zeros. And the transients, this means that C1, B1 it means this vector that's inside the brackets here can be expressed in B coordinates this way. like that. And this is zero vector. So what we have is this thing is equal to the zero vector, but not all these C's are zero. Remember, CI's are not all zero, and so we must conclude that the vectors, even in the original space, is a linearly dependent. Because there are non-zero C's, such that the linear combination of this is zero. This is a very, very important theorem. Because what it says is if you've got any vector space and you've got n things in it as a basis, there are n elements of basis. That means if you ever have any set that's got n things or more, I'm sorry, n plus one things or more, that is automatically linearly dependent. So if you've got a 10-dimensional vector space, if you take any collection of 11 elements, it's automatically a linearly dependent set. So this buys us some stuff. And here, and I'm going to prove these theorems too, but now this first one really paves the way. Everything after this is much simpler now that I know this fact. So theorems. If B has a basis, B is a vector space of n elements, then any basis of B has exactly n elements. This is a very important theorem, and it's one of the things that makes vector spaces and thinking about things from this point of view important. Given a vector space, it may have a whole bunch of different bases. If you look at R3, which is if any of you are in Calc 3 or will be there, this is a big vector space that you play around with. It has infinitely many bases, infinitely many. But whatever basis you pick will always have three things in it. Always. So, suppose B1 and B2 are both bases. And we'll assume for finite here. Actually, this theorem is true actually for vector spaces with an infinite number of bases. We will restrict ourselves to only considering finite dimensional vector spaces. Suppose that B1 has n vectors and B2 has n vectors. Anybody see how we used the previous theorem to show that the two sizes are the same? On the previous theorem, since B2 is basis, any set of more than n elements, more than n vectors, is linearly independent. Linear. So V1 is basis and it's got n vectors in it. The previous theorem tells me that if I have any collection of vectors that has more than n elements, it's linearly dependent, right? Everybody agree with that? So V2 is basis too. So its m vectors have to be linearly independent. Everybody agree with that? If V2 is basis, then the elements in V2 have to also be linearly independent, because the basis has to be a linearly independent set. Can somebody tell me what that tells me? Yes. Well, actually, so far, that's what I know. M has to be less than or equal to n, because I know that this has n elements in the basis, and I know that V2 is a linearly independent set. That means that the number of things in V2 cannot exceed n, so it's got to be less than or equal to n. Agree? Now, reverse roles of V1 and V2. So change every V1 into a V2 and every V2 into a V1 here, and we get n is less than or equal to m as well. And I don't know much, but I know if I've got two integers and m is less than or equal to n, and n is less than or equal to m, what can I conclude? That. So that means that two bases have exactly the same number of elements. Any questions on that? Okay. Let me get kind of a definition here. Yeah. Think here's a vector space. And its basis has a finite number of elements. Well, it's explained by a finite set of vectors. M, B, then D is a finite, it's called a finite dimensional vector space. If a basis of B has n elements, we say then B is equal to n. And we say the zero vector space remember, the zero vector by itself is a very silly vector space, but it's a vector space nonetheless. And there are no linearly independent elements in that set. And so we say dimension of zero, the vector space zero is just zero, because there are no elements in these spaces. If dimension of B is not finite, Yes,
Why is it? Don't you need at least like one zero vector to,
what's that mean?
don't you need the zero vector to make a basis for the zero?
The
space?
zero vector never, there's a technical problem with that, so I understand what you're saying. So his argument is, well, why don't you just take zero to be the basis, right? But there's a technical problem with that, because zero as a standalone vector is not linearly independent. Because one times the zero vector is the zero vector, and one is not zero. So if you want to get into the technical, logical kind of under the hood, then the the zero vector space is considered to be generated by the empty set, right? But don't worry about that too much. It's just, zero vector space is pathological. There's something wrong with it, so it actually has no basis. If the dimension of B is not finite, we say, guess what? It's infinite dimension. So, for example, I'll reiterate that. Dimension of Rn is equal to n. And I'll give you a basis for Rn. How about the standard basis? That's a basis for Rn. It's easy to show that this is both linearly independent and it spans all of Rn. This is certainly not the only basis for Rn. There's a lot of, here's another one, by the way, fun. Just one, the two leading ones, the three leading ones, and then all the way down to one. This is another basis for Rn. It's not too bad to show that that is a linearly independent spanning set as well. All right. But the magic of the previous theorem tells me that any two bases Rn must have the same number of elements. So that's good. And there are many more exotic bases. Yes. Remember what this was? Polynomials of degree n or less. Might be easier to see if I give somebody give me a basis of this. Yeah.
1x, then all the way up to x to the end.
There. And this answer is kind of an open-ended question that I think you answered a little bit earlier. This shows you that the dimension is actually n plus 1, because if you sort of count with the powers, 1, 2, 3, n, but I left out that, so there's n plus 1 elements of this basis. By the way, can somebody give me an example of a vector space that is not finite dimensional? Hold on. Yeah.
Like an infinite series or something?
What's that now?
An infinite series?
I think that'll work. We'd have to make that a little bit more precise, but you can do something. Yeah.
We use that as the trans zeros.
So you just make an infinite string. Yeah. So if you've looked at one of those old quiz problems, right? That's a good example. Here's another one. Here's one that's like maybe the most familiar. How about all polynomials with no restriction on degree? I can be as big as I want, right? Polynomials are not Sprengel functions. The dimension of this is infinity. Anybody want to give a basis for that? It's just like this, just don't stop. That's a basis, but you can only use finitely many things at a time when you write down a single element. Anybody want to know, give another example of an infinite dimensional vector space? What's that?
All continuous functions.
Oh, that's exactly what, that's a good one, right? If you look at all continuous functions, which is bigger, polynomials are all continuous, if I remember out, right? All continuous functions much bigger. You got all kinds of crazy crap in there. You got sine x, cosine x, you've got the absolute value of x, all kinds of stuff in there. Anybody write down the basis for that? If you could write me down a basis or give me a formula for the basis of all continuous functions, just slip it up to me in an envelope and I'll write your name down. I'll give you an A and just go down to the term for the rest of the semester.
I'll slip it to you in an infinite envelope.
Yeah, that's right. It'd be a very big envelope. In fact, there is a basis for continuous functions as well, but you're not going to be able to construct it. In fact, there'll be an infinite number of elements in the basis, and I'll make it worse for you. The size of infinity is much bigger than this size. It's actually bigger. So just finish the course. Don't try to write it down. Okay, any questions? Okay. We got just a couple more theorems here to talk about. The next theorem, we're kind of building up how this stuff works. Let me the finite dimensional vector space. And W inside of a subspace. So remember, what do I know about W, right? Since it's a subspace of the bigger, perhaps bigger vector space V. I know zeros in there, right? Zeros in W, and I know it's closed under addition and it's scalar multiplication, right? And W could be silly, right? W could be all of V, or it could be zero vector, right? But that's the situation we've got here. Any linearly independent subset of W can be expanded to a basis. Okay, so let me clarify what that sentence says. What this says is, okay, I've got what this sentence says is following. Here's the situation. Here's V, whatever it is. And we've got the subspace in here, W. Now, this is sort of a little baby vector space sitting inside the parent. And what this says is if I have a linearly independent set, so I've got these, say, 4 vectors here. And what this means is this linearly independent set is already a basis for W, maybe. And even if it's not, I can throw in a few more vectors and make it be a basis, right? Just by adding some stuff. So that's what I mean by expanded to a basis for W. I start with some vectors in there that are linearly independent. If they're already a basis, good for them. If they're not already a basis, then I can throw in some more until I get a basis of W. And by the way, I'm going to throw in this last comment because it is kind of an important comment. If I have little space inside a big space, what do you suppose the relationship is between the dimensions of those two spaces? Oh. Look at my picture here. Which vector space is bigger? B. What do you suppose should be? Both of these vector spaces, V and W, have bases, right? What do you suppose the relationship is between the dimensions? That is the number of elements in the bases. Yeah.
Use greater than.
The number of elements in the basis of W is less than or equal to the number of elements in the basis in the big space. Everybody okay? Okay. In particular, let me also point out that if you have a linearly independent subset of W, you can actually keep adding stuff in this until you get a basis of D, but you might have to put in some extra vectors that are outside of W. Okay. You may think of a strategy of this. This is actually a very fundamental and important theorem about vector spaces and linearly independent sets. Basically, if you have a linearly independent subset of any vector space, you can just get your shovel and start shoveling new vectors into there until you grow it to a basis, right? And actually, my little shoveling action shows you how the proof works and the following things. So So let me set up the players. Suppose I have a set of linearly independent vectors. Okay? And let's let B now B's vector space, and I did say it's finite dimensional. Yes, I did. So it's got some basis, right? Okay. Through what we've learned today, can anybody tell me what the relationship is between N and K? Anybody know what should it? So here's my basis for B. It's
Should just be, N is greater than or equal to.
the number of elements in my basis B has to be greater than or equal to K. Why is that?
K was bigger than subspace.
Well, right. What did the first theorem say? If you have a basis for B, now we've got it, then any subset of B that has more than that number of elements has to be what? It has to be linearly dependent, right? So every set that has N or more elements has to be linearly dependent, right? This set is linearly independent, right? Agree? That's what we said here. So the number of elements in it must be less than or equal to the number of elements in the basis. Everybody okay with that? Okay, so let's get the shovel out. If W1, W2, WK is already a basis for W, then none. Because here's the way I expand it to a basis, I just leave it alone. If not, if it's not a basis, then can somebody tell me what that means? I mean, what is a basis? It's a linearly independent set that what? Spans all of W. So I've got a linearly independent subset of W, already got that covered, right? If it spans it, it's a basis. If it's not a basis, that means there's something left over in W that isn't covered, right? So if not, let the vector X not span vectors W1. And now throw this in here. And this must be a larger linearly independent set. Anybody explain why it's linearly independent?
Because X is not a combination of other.
That's exactly right. Because if we write down I claim that all these C's are zero. Well, in the first case, let me point out that if this C is zero, then the rest of the C's are zero. Everybody agree with that? Because we know that this set was already linearly independent. So if this C is zero, then the rest of the C's have to be zero. So that means this C is not zero. And if this C is not zero, that means that X is a linear combination of the others. But we've already said that X wasn't in the span of those. So this has to be a linearly independent set. If W1, W2, WK, and X span W, this spans W, then because now I've just added X to this, and I've got the basis. Okay. What if not? Then do the same thing over again. If not, find a Y in W, not span, and make the larger linearly independent set W1, WK, X, Y. If this is a basis, then you're done. And if not, add a third vector and so forth and so on. Everybody okay with it? Now, my question is, yes.
Show how we know if like the X vector, if adding X vector is not the basis.
What's that now?
Like if we add the X vector, the first thing we did, can you show how we know that that wouldn't be a basis and then we have to keep going?
Oh, well, so here we're hitting a fork in the road. maybe it is a basis, and that often happens, right? If it's a basis, stop, because you're done. If it's not, then just like before, that means there has to be something left over when you look at the span of these vectors. Say why, and I throw that in, right? If this one now spans, then quit. And if not, then find something that's not spanned by it and throw that in. And so we're building, that's what I mean by the shovel. I keep throwing in new stuff that I wasn't covered before. Now, here's the $64,000 question. Why does this process stop? Right? What if it goes on forever? That could be a problem, right?
It's bounded by the elements.
That is correct. This set of elements right here, there's only n elements in the basis of V, and V is the daddy Mac over here. That means I can never exceed n plus 1 elements in this set, because it would automatically have to be linearly dependent, right? So this stops at or before we reach n elements of set. Because V has a basis of n elements, any set of n plus 1 elements has to be linearly dependent. So I know that this process eventually has to stop. That's actually something that's really important for engineers and computer scientists, is knowing that a process or an algorithm will terminate. Okay, any questions? All right, so theorem. This is called basis theorem. Suppose B is a vector space, and the dimension of B, I'll call it K, is bigger than or equal to 1. This is a really groovy theorem. So suppose that on the surface of it, I know that V is a vector space, and somehow God has told me, or through some other means, I have figured out that the dimension of this vector space is exactly K. Okay. Then, one, any collection of K linearly independent vectors in V is the basis. That is cool, because if I know the vector space is of dimension K, if I've got any K linearly independent vectors in there, it's automatically a basis. Any collection exactly K elements in V that span in the basis. That is super groovy cool, because what that says, so I've got kind of a two-headed thing here. If I know out of the starting gate, if I know the dimension of the vector space is K, and I have K linearly independent vectors, basis automatically. If I have that the dimension is K and I have exactly K elements that span this vector space, it's a basis. They're forced to be linearly independent. This is a very cool and a very useful theorem. So obviously I'm not going to prove this, but see if you can figure out why this is true. It depends basically on the results that we had today, and it's sort of like the shoveling action, but it's actually easy. Any questions? Okay, your quiz will be posted later today. Other than that, I'll see you guys on Wednesday.